Yes. Okay, so I think we can start. How is the sound? Is it good? Yeah? Okay, great. So this lecture is about economic evaluation. The goal here today is to examine how we do in economic analysis to evaluate possible policy options. And the next lecture, which will be in a few weeks, we'll look at the policy options in more detail. Okay? So remember where we left last time, where we introduced the notion that we have a big collective action problem in the environment in various ways for different parts of the nexus, but this is a pervasive problem, so that means we need some public intervention or some collective way of dealing with that. And so we need to evaluate these options before we do something, right? That's the question. And I added, and I want to flag again, that inequalities should not be forgotten in this analysis because they are part of the nexus in essentially everywhere here. Now, to be frank, there is one part of the nexus where economic analysis is not strong. I already said it last time, is this part here about the value, the intrinsic value of nature and other species and all that. This is still very much work in progress. Actually, I'm working on that myself now, but so I won't talk about that here today. It's another story. Okay, so first point, you have two main methods in evaluation of policies. One is cost-effectiveness analysis, and the other is cost-benefit analysis. So what's the difference? Cost-effectiveness analysis is less ambitious. It takes an objective as given. So if you think, for instance, of the climate problem, it takes a target temperature or a target concentration of greenhouse gases in the atmosphere, and it says, okay, let's try to find the least costly way to do that, right? Cost effectiveness, let's look for the least costly way to achieve the objective. And you have cost-benefit analysis, which is more ambitious because it also questions the target itself. It says, what is the optimal target? And so in the example of climate, what is the optimal temperature target? What is the optimal concentration target? And how does it get that? Well, by weighing the cost and the benefits of the various possible options. And in the case of climate, to continue this example, what are the benefits of climate policy, climate mitigation? Well, the benefits are come from avoiding the climate impacts. Right? And so you have a big difference between the two approaches in this kind of application. If you want to do cost-effectiveness analysis, you take a target temperature, let's say 2 degrees, and you look for the least costly way to do that. You don't need to know about the climate impacts. That is not something you need to picture because it's not part of what is relevant to your analysis. Whereas if you do cost-benefit analysis, that's very relevant. And the uncertainty we have about climate impacts is something that induces uncertainty about the right temperature target we should adopt. Okay, so we'll come back to that again in the future, but now I want to explain one key thing, which is that in both cases, whatever you do, whether it's cost-effectiveness analysis or cost-benefit analysis, you have to deal with the problem that the costs and or the benefits are spread over many people, right? They are spread over many people, and this issue of the distribution of costs and benefits requires that you have a way to, you need to be able to trade off the conflicting interest of different people. Who should bear the cost and who will receive the benefits? That's very relevant, and so you need to do that. And we have in environmental policies, which are generally long-term policies, we have two dimensions. We have the inequality across people, and we have the time dimension. So we have the fact that some impacts are very much in the long term. So what I'll do in the rest of this lecture is to focus on these two aspects. How do we deal with inequalities? How do we deal with time, the time dimension, especially when we have long-term impact? Okay? Is that okay? Any question or any comment at this point? No? Okay, good. And so let's focus on inequality. So there is a frequent practice, and I would say a too frequent practice in cost-effectiveness analysis and in cost-benefit analysis together, which is just to add up the cost and or the benefits without worrying about the distribution. So you just add up everything. You compute a big cost, or you compute the net balance sheet of total benefits minus total cost, and that's what you do. Okay, so there is an underlying principle behind that, which is the idea that a dollar is a dollar, and you just add up all the dollars that you have in your analysis. The question is that okay? Right? And so many non-economists actually despise economic analysis because they dislike this way of adding up the dollars that accrue to different people. And indeed, it means in practice that you will, for instance, look at these examples in this sort of situation. If you have $100 to give to someone, it doesn't matter if a dollar is a dollar, it doesn't matter to whom you give it, whether it's a rich or a poor person. If you are looking at a problem of pollution in a particular area, and especially there is a polluting facility that needs to be located somewhere, you can put it in a poor neighborhood or in a rich neighborhood. Well, okay, if you look at what are the corresponding costs for the various neighborhoods, well, the poor neighborhood will have a willingness to pay to avoid this nuisance. That is likely to be less than what the rich neighborhood is willing to pay. And so if you just add up the dollars, you'll say, okay, let's locate the polluting facility in the poor neighborhood because the cost is less important there. And finally, if you look at people's willingness to reduce risk to their life, typically the rich have a greater willingness to pay for their safety than the poor, and that can induce policy conclusions like, for instance, you should have greater safety in planes than in trains because the average income of flight travelers is higher than the average income of train travelers. So I've put the risk of the various modes of transportation per mile, and indeed you see that the risks are unequal between air and train, and I've put some other risks as well. But yeah, so it's not as if this was not controversial, but we see indeed some differences in the real world. So this is pretty controversial, right? This is shocking to many people. And so the question is it really all economic analysis has to say about that, right? That's the question. Is it all it has to say? Well, if you look at the practice of the US administration over the last decades, it has a tradition which is the following. When you do the computation of cost-benefit of various policies, whether it's in transportation, safety, or in other departments, what you should do is to adopt this approach. So a dollar is a dollar, computing the numbers, but you should have an appendix or an extra section that describes the distributional impacts of your policy. Right? So you don't put that in the numbers directly. So you have the raw numbers which just add up dollars, but you need to have a description of who is willing to complain, right, in the electorate. That's the idea, more or less. But there is no recommendation that all the numbers should be put together in some way, right? That the recommendation has always been not to do that. And that's contentious because there is a way, which is quite standard actually, to put all the numbers together and to give different values to different dollars. So how can you do that? Well, the orthodox method is to adopt what's called a social welfare function. So let's do a little bit of math, but just a little bit. So I'm sure you've been familiar with functions for at least since high school, f of x. But here you have a function which is multivariate. So it's a function that depends on x, y, z. And these various arguments are the well-being of the people in the population. So if we have n people in the population, you list the well-being of all these people. And so that's a function that looks complex because it has multiple arguments, but it can be simple. And the simplest one is the so-called utilitarian social welfare function that is just adding up the well-being of the people, right? And it's called utilitarianism because it was essentially proposed in this way by Jeremy Bentham, an English philosopher from the turn of the 18th, 19th century, who is, you can visit him if you want, he is still in this shape at University College London in a showcase. In his will, he said he wanted to be always there and always be carried to the meetings of the society he had created. So I don't think he is still carried. Now he stays in the showcase, but you can still see him. So he was really insisting on the fact that we should evaluate everything in terms of the consequences on people, and especially the utility of things to people. And so this term utility has become really something that has stuck, and utility is now used also to talk about how well off people are. So U of I is now called the utility of individual I, which is a bit of a strange way of using the word utility, but it means it's how well off this individual is, right? And this utility, what's important is that the utility of an individual, so the well-being of this person, will itself depend on what this person has, for instance, in terms of income, consumption, wealth, and so on, right? So that will depend on the situation of this person. So it's itself a function. So we have a utility function, and if we make it depend on income, wealth, or consumption, these are dollars that we put in this function, right? So you see how it works. So we'll put dollars as arguments of these utility functions. We'll add that up, and that will give us the social welfare. Is that clear? Is there any ambiguity about the way this works so far? No? Everybody happy? Okay. So how do you choose your utility function? So if you just make it a function of something like consumption in dollars, okay, so let's imagine this is C means consumption in dollars. A standard way of giving different values to different dollars is to use a function that is concave. So Professor Pacala likes the word curvy instead of concave, so we have a big disagreement about that. No, I don't care at all. So curviness is totally okay, but the technical term is concave, and the shape of the function when it is concave is like this. And you see the point of having a curve like that is the following. If you give an additional dollar, so these two arrows here are the same size, so you give an additional increment to someone in dollars, the same. If this person is at a low level, that has a big impact on his utility, right? That's the function U of C. If this person is high, that has a small impact on his utility. Okay, that's the idea of having, and this is usually called diminishing marginal utility. So marginal utility is just essentially the slope of what you get from an additional dollar, the slope of this graph. All right, and so when you have this, you can talk about things like transfers between rich and poor, right? So same things here, but now imagine that we start from the two extremes of this distribution. You have a poor who starts here, a rich who starts here. Let's imagine that the rich makes a transfer to the poor. What does it imply for the sum of utilities? Well, you can read it on this axis. You have the utility impact. So the utility impact for the poor is greater than the utility impact for the rich. For the rich, it's a loss, of course, but small. And so the sum of utilities will increase. So if your criterion is the sum of utilities, you will say that such a transfer is desirable when your function is curvy, when your function is concave, right? If you had a straight line, you can see if you had a straight line, you wouldn't care because the gain in utility for one would be exactly the same as the loss in utility for the other. So it's the curviness of the function, the concavity of the function that really makes a difference here. Is that clear? Yeah? Yeah? Okay, good. And so one other question I'd like to mention briefly, and I'll be quick on that. We can have conversations about it if you want. This is a whole topic in itself, but one issue is, what is this utility function about? How do you define it? And so there are people who say we should look at empirical data, and there are people who say, no, this is an ethical choice by itself. And so the empirical option, you have different empirical options, but one prominent one, especially lately and fashionable in economics, has been to look at subjective expressions of satisfaction or happiness by people. And my colleagues Angus Deaton and Daniel Kahneman have really explored that. And they have found that indeed you find some curviness when you do that. So here you have, I'm sorry, this is pretty bad. I don't know why. It's much better on my screen. So let me explain. So these are, sorry. Okay. Yeah. So these are levels of GDP per capita at a given year, which was 27, I think. And these are the average satisfaction that people expressed in various countries, and the bubbles here that look like they have exploded already are representing the size of the population. So China is here, the US is here, and so on. And so this represents the average satisfaction as it correlates with the per capita GDP in the countries. You see, it is a straight line, but the axis is actually a logarithmic axis. So every additional step on the axis doubles the level of income. And so if you were to put that in terms of ordinary axis of dollars, then you would have a curviness that corresponds to that of the logarithmic function. Okay, so you do find something like that. And likewise, they have done something in cross-section in the US, where they have looked at, so you have a straight line here which corresponds to what's called ladder. And ladder is again a satisfaction question. How satisfied are you with your life? And it's a ladder, it's called a ladder question because the question refers to a ladder where it's between 0 and 10. And so you have the lower rung and the higher rung. And the question is on what rung of the ladder are you? And so again, you find more or less a straight line for the ladder question. And again, you have logarithmic scale on the horizontal axis. You have other curves here which flatten out, so that would lead to a greater curvature in some way, but this is, these are curves about feelings, how people feel, right? So it's more about the hedonic idea. And so you have indeed these two notions. Either you focus on people's judgment about their life, how satisfied they are, or about their feelings, a more kind of hedonic notion. Okay, so that's one approach. And there is another approach which, one thing I want to mention is that if you look at long-term impacts, this approach has potentially a big problem, which is that we do have a few long-run data about these satisfaction scores, and they seem very stable over time. So people, and you can guess why, people tend to adapt to the situation, their reference points change with history. And so up there you have the flat curve here is average satisfaction in the US. The curve that goes up is GDP, right? So growth of GDP doesn't seem to be connected to what happens to satisfaction. And here you have also flat curves for other countries in Europe. Okay, so this is this paradox, fact that it looks very flat when you look over long-run periods, has been pointed out by Richard Easterlin. So it's called the Easterlin paradox. All right, so that's potentially a problem, especially for very long term. If you look at, for instance, climate policy, the effects are over 3-4 centuries. So that is potentially a serious problem. Now you have another approach which says, okay, it's an ethical issue. So the curviness of the function should be really your choice. You should decide how much priority you want to give to the poor. Remains another question, which is, what do you put in the function? Is it just consumption in dollars? What about other dimensions that are non-market dimensions like health or social status and things like that? And so there is some work that has been done along two lines. So one is saying essentially let's try to rely on people's preferences still to some extent, but construct something like what's called a resource index. So it's essentially an income index but adjusted for quality of life, where you take account of how people would like to correct their income for the advantages or disadvantages they have in other dimensions like longevity or unemployment status. I've done some work with OECD colleagues doing that. So you have curves which represent something like this adjusted income, and you can compare these curves to GDP, and you see they fluctuate very differently. And especially if you look at countries that have suffered a lot from the financial crisis like Greece and Spain, you see the dramatic drop in these curves that is much worse than the drop in the GDP curve that they have. Another famous example, which is not using people's preferences, which is more objective, is something called the Human Development Index that has been developed by the United Nations Development Program. And it also incorporates other dimensions, longevity and education, in the analysis, right? And you get things which are also, you can look at different regions of the world and how they evolve. And that's another way of looking at it, but it doesn't rely on people's preferences. So there are debates between these various approaches. I will, unless there are questions or comments, I will go quick on this and continue. Is there any question or comment on these various approaches? So the big thing here that you should remember is there is an issue. Should you rely for this curviness of the function, should you rely on empirical data, like satisfaction data, or should you say, this is the policymaker's choice, this is how much priority you want to give to the worse off in the population? There are other ethical issues I'd like to mention briefly. So I said we have this social welfare function that depends on the utilities of the people, how well off people are. And you could say, okay, should we put something else than how well people are? Are there other relevant arguments? So if you say, no, it's enough to know people's well-being and nothing else counts, then you are a so-called welfarist. Okay, that's the welfarist approach. If you say, well, there are some other things that may count. For instance, you may worry about the procedures by which the outcomes are brought about. Then you may enter into a different territory, something that's non-consequentialist, for instance, or non-welfarist. And I will leave further discussion of that to the ethics section of the course. But that's something that is not prominent in economics, but should not be forgotten. And again, non-human animals are not part of the picture in standard analysis, and at some point we should put them in. And another thing is that I will focus here on the sum of these utilities, which is the simplest function. But of course, you have other functions which are different. And especially this is very relevant when you look at risk. We won't deal with that here in this lecture, but this is something that is also important. So I'd like you to put out your clickers now, if you don't mind, to elicit your views about how much priority we should give to the worse off. Right? To see what we have in the room in terms of attitudes toward this question of priority. All right? And so we'll do that with a kind of concrete example. This is called the leaky bucket thought experiment. How does it work? So imagine you have a guy who is earning $80,000 a year. Another guy is earning $40,000 a year. And we imagine making a permanent transfer of $1,000 from the richer guy to the poorer guy. But there is a potential cost in the transfer, right? There is a leak in the bucket. And so what the recipient gets may be less than 1,000. Okay, the rich always pays 1,000. The poor may get less than that. And so depending on the cost, you may approve or disapprove of the transfer. And the question I'm asking you is to select the option corresponding to the level at which you stop approving the transfer. Okay, so if you dislike the transfer right away, even if there is no cost, you choose A. If you accept when there is no cost, but you don't accept when there is a $100 cost, then you choose B, and so on. Right? So you have different levels, and you get for full clarity, you get what the recipient is actually getting because of this cost here. Is that clear? Everybody okay with the question? Is there any ambiguity about the question? No? Yeah? So this is a matter of preference. So there is no right or wrong answer. I'm just trying to elicit the attitudes in the room about this issue. Okay? And we'll see how it compares to standard numbers later on.
So when you pick what you're not willing?
Yeah, where you stop. Okay? Where you say, oh no, now that is too much for me. All right? Yeah. Okay, if you want to accept everything, then perhaps you can choose this one. Let's bundle together the people who would accept always, no matter what. Okay? Then you can choose this one, the last one. Right? Okay. Is that clear? Yeah? Can I start? Okay, so go ahead. Yeah? All right. Sounds good. Okay, so let me stop now and look at the results. Okay, so C and D are prominent. Okay, fine. So let's keep that for now, and we'll come back to it to see what it means. So how do you analyze that concretely before comparing to what economists have been doing? So how can we use these results to discuss, to calibrate the curviness, the curvature of the curve, right? Well, so this is the example. You have a poor who receives from a rich, and you have a greater gain in utility. So that's when you have no cost. And so for this particular curviness, you can try to find out at what level of cost of leak you start saying that this is a good transfer. So here, the gain and the loss are approximately the same, and so that corresponds to a certain size of the cost. Okay, and so that gives you. So you see, if you had a more curvy function, you would accept a greater cost because the slope would be greater here. Right. So that's how we can relate the answers to this leaky bucket thought experiment to the curviness of the function. Okay, that's the key idea here. So if you get that, that's great. All right, now let me talk about time. So there is a frequent practice in the world of economic analysis, which is to discount the future dollars at a rate that is more or less similar to things coming from the market rate. And the values that you find actually are quite diverse depending on what people take, but it can go from as low as 1% to as high as 7%, and I'll say more about that. So how does this discounting stuff work? It does the following. So let me take as an example 1% discount. So what it does is consider the evaluation of $100 in 2030. How much is that worth now if we discount, right? So if we discount at 1%, what we have to do is to do it year by year to bring it back to today. And so if you look at the value of that in 2029, that will be 100 divided by 1.01, which corresponds to 1%. Okay, and that gives you this value. And when you go one more year ahead, 2028, then you'll take what you had the year before, and you again divide by 1.01, which corresponds to taking the initial value, 100, divided by 1.1 to the square, right? And so if you continue like that, when you arrive in 2020, you raise it to the power 10. And so raising to a certain power like that is really this notion of compound interest, and that's how discounting works, okay? And this is a quite powerful method in order to compare values across different periods of time. Do you understand how it works? How to do the computation? Yeah. If you take a loan, for instance, you have to think about this sort of computation in a similar way. Okay. Now, is this way of comparing, of putting together dollars from the future and the present, is that economically and ethically okay? And that's, again, the question that I'd like to look at with you. And in order to do that, I'd like to look at a concrete example, which comes from climate, because today is a record temperature, so that's, again, an example which is nice to take. And so I've taken the prominent model dice that Bill Nordhaus, who got the Nobel Prize for this work last year, had created. So you can go to his website, you can find the Excel sheet, and you can compute scenarios. So I've done a simple scenario. So there is a baseline. So when there is no particular mitigation effort in his model, this is the blue curve. And what we have here is over 5 centuries, we go to 2500, over 5 centuries, we have the consumption per capita in $1,000, okay, at the world level. And so the blue curve is the baseline with no particular mitigation effort. And the red curve is what we would get if we had a very aggressive policy that reached 0 emissions in 2030. Okay, very aggressive policy. If you look at these two curves from afar, you say, okay, it looks like a no-brainer. The mitigation path, the red path, is much better than the blue path, right? Well, but you have to be careful because the curves are a bit thick, and here the red one is actually below the blue one. So there is a cost in the beginning, and the cost is actually, so this is the same thing, but this is just the difference between the two curves. Okay, the difference between the two curves is actually negative up until almost the end of the century. Okay, so we have about 80 years of suffering before we can enjoy the benefit. Okay, so the benefit comes the avoided climate damages, and the cost comes from the mitigation efforts. Yeah. All right, and so these are the the raw dollars without discounting, and you see they are quite substantial because when you are in 2300 or something like that, you have values which are already above. So that's the difference between the two scenarios, and the difference is already above the current value of the consumption per capita in the US. Okay, so that means that the difference is sizable, is very big. In the future, it is bigger than the total pie we have now in this country, right? So, and we are talking about a rich country, but that's for the world level. So this is a big positive difference in the future. What happens if we discount that? So we can construct the same graph with the discounted values. So here the red curve is a curve that corresponds to the same thing, but with the discounted term. So divided by 1, so with 1.5 discount, it means I divide by 1.015 up to the time difference between that future period and now, okay? And so the blue curve now here is the undiscounted, the raw dollars. I had to change the scale because otherwise you wouldn't have even seen the shape of the red curve, right? And so we now understand that the average cost in raw dollars are about $1,000 at the worst point here. When we discount, we reduce the value in the future, and that becomes very, very important in the far future. Right, so these big differences that we have in the far future become negligible when we discount. And that's with a very, very low discount rate. That's the discount rate that was advocated by Nick Stern, but this is not the most frequently used one. If you take 3% discount or 4.5%, then you get things which are even, I have to change the scale again, otherwise we don't see what's going on. And so at 3% discount, we have this curve. At 4.5% discount, we have this curve where the benefits appear almost negligible. And so if you want to decide whether this aggressive policy is a good thing or not, if you just do an addition of all these dollars, you see, you would decide if you are at this discount, you have to compare the area below this curve here, which is positive, to the area above this curve here, which is a negative area. So you make the difference between these benefits and these costs. You see the benefits outweigh the cost here for a low discount rate. But if we have a higher discount rate, then the benefits start to disappear. Already at 3% discount, the area below the curve here looks smaller than what we have here, right? And so the more you discount, the less the benefits in the future appear interesting. And if you go to 7%, then the benefits just completely disappear because what happens in 1 century essentially doesn't exist at all. Okay, question? Yeah?
The y-axis of the original.
Yeah.
Why are you measuring consumption as the measurable of the
Yeah, so that's what the model is doing. I'm just taking what he does. So it's a rough idea. We just look at people's standard of living in consumption per year in dollars. Yeah, that's a kind of rough measure. As I said, if it would be better to adjust for additional things like longevity, for instance, right, and this sort of thing. But at least in the first approximation, it's good to use consumption, right? It's the first basic thing. Yes?
Does that consumption per capita change with the discount rates? Like the...
No. So the raw numbers, the initial curve remains always the same. It's just the discount term that multiplies these raw numbers that is changed because of the discount rate. Right? This is the only thing that changes. And I had to change the scale because otherwise you wouldn't see the curves. They always become smaller and smaller and smaller. Right? That's the problem. Okay, so that's the example. And the question is, what do we do with that? So I don't know if you know, but there is an interesting political situation in this country. And so there was an executive order by the president 2 years ago that disbanded the interagency group that was computing the social cost of carbon. And this was the main user of this approach, comparing, so the social cost of carbon is essentially computing the present value, using the discounting method, present value of the climate damages, the negative impacts of emissions, right? And so this group was used to produce this kind of table that gave you an idea of the cost of an emission. And they were using levels of the discount rate, which were, so 3% was the focus of this group, and you had a sensitivity analysis around that. All right, so that's no longer available. You can still find it. So I give you the links where you can still find the documents, but it's no longer on the EPA website. What's interesting is that the executive order of 2 years ago referred to the fact that we should go back to good practice, and good practice was defined in 2003 by a circular. And so I give you all the elements so that you can judge by yourself. You can go to this circular, and here are excerpts from this circular that says that we should use 3% and 7%. And it says 7% is mostly for things which are reallocations within industries. 3% is the relevant rate for impacts on consumption, on households. And especially so there is an additional special section on intergenerational impacts where it says we should even look at things between 1% and 3%. So a lower discount rate when we look at very long-term intergenerational impacts, right? So that's what the circular was saying. I leave it to you to judge what that means in terms of the justification for the presidential executive order. Okay, so what should we do? Okay, so as I did for inequality, I said the dollar is a dollar. We can do better than that. And here, this row discounting method, can we either do better or justify it on sound basis, right? And so again, the idea is the same. Take a social objective that is consistent and reflects something that takes account of the interests of the various populations. And so in the case at hand here, what you can do is go back to BenFam again and take a discounted utilitarian approach. So it's called discounted because what you do is the following. So this big thing here means you take the sum over different periods of time. And to simplify things, for a few minutes, I will neglect inequalities within generations. I will do as if every generation had full equality inside it. And so what we have are the consumption levels of various generations. For the present, it's 0, and then we have 1, 2, 3, and so on. We have the utility of this for each generation, and then this is a per capita thing. So we multiply by the number of people. LT is the number of people in that time. And beta is a parameter that reflects the possibility that the future counts less just because it is the future. So beta is less than 1 when we have what's called pure time discounting. So somehow beta is introducing a discounting on utility itself. And this is very contentious. So some people say, yeah, we should just respect the fact that people are myopic. The future is the future and counts less just because it is the future. So this is dubious, and most people dislike this justification. But there is another justification which is less contentious. The future may not just be there, right? So there is a real risk of extinction. And so if that's the case, then indeed, once we are no longer there, that doesn't count anymore. Right, so that's potent, but it's a justification for a very, very low discounting there. So the beta could be very close to 1 normally if it's just that. And finally, you have this U function, which is just what we talked about. And you can decide whether you want to rely on subjective utility to decide how curvy it should be, or whether you should decide on terms of ethical priority for the worse off. All right? Okay, so how does it work in terms of discounting consequences? Well, the way it works is the following. You take this function, and to simplify things, I forget about the population because otherwise I have populations at numerator and denominator in my computation, so it's just a hassle and it doesn't change anything to the conclusion. So imagine there is no change in population over time. And so if you add $1 to consumption now, what is the impact on your social objective? Well, the impact is just it changes the utility of the first period. You have C naught in the first period, period 0, plus 1, and that's it. Okay? And there is no beta because beta to the power 0, that just disappears, it's equal to 1. Now, if you look at the future, if you do $1 more in the future in period t, then you have something that is added to CT, and you have the beta t which appears, which may reduce the impact, right? So we may have 2 reasons to discount a future dollar, to consider that it's less important because its impact on W on social welfare is less important. One reason is that we may have a beta less than 1, especially if we believe extinction is likely to happen. Not so important. The more important thing is that we may consider that adding $1 to the future is less important because the future will be richer than us. Right? And so the marginal utility of the future, the slope of the utility function may be less than now, and that's a reason to discount the future dollars. Right? So indeed, we can justify discounting the future dollars. Perhaps not so much because it's in the future, but because the future will be richer. That's the key consideration that I wanted you to understand. And there is an even more precise formula that's being used to combine all these considerations together. So I won't do math and try to justify the formula in detail, but you can understand the meaning of the formula and why it is intuitive. So this formula says the following, and it's due to Frank Ramsey, who was a young mathematician who died very young, unfortunately, but who did a lot of very brilliant things in various areas. And one of them is this analysis of growth. And so he had this idea that discounting future dollars, right? So when we look at future dollars, what kind of discount rate should we use for that? Well, that will be the addition, the sum of two terms. The first will be a discount rate on utility, so that corresponds to the beta term in my social welfare function. And as I said, it should be potentially quite small, but that's a term that is more or less equal to 1 minus beta, if we refer to that function. Then there is an additional thing that corresponds to how richer the future is, but here we have two things that combine together. How richer is the future? That's the first question, and that depends on the growth rate of consumption. Okay, GRC here is the growth rate of consumption between now and then in terms of annual average rate. And CIA is not a federal agency, it's the coefficient of inequality aversion, which represents how curvy your function is. Because if the future is richer, that makes it less of a priority. The more we care less about the rich people, right? And so the more curviness you have, the more curvature you have in your function, the less you will care, and that multiplies because the two things compound one another, right? And so that's how it goes. And let me illustrate how the main economists who have used this formula have picked numbers to fit it. So if you take the Stern review on climate change, he took a very low level for the discount rate on utility, so a beta equal to 0.999. And the idea was this is the extinction rate, which is still, I mean, this is 1/10% over a year, so that's still a lot. That gives us about 10% of being extinct by the end of the century, so that's a bit scary. So probably it's a bit exaggerated, but nevertheless, it doesn't make a big difference here. It's a very small number. That doesn't change much to the final number. This is the assumption he made about the growth rate, so 1.3%. Okay, and he took a rather low value for the CIA, for the coefficient of inequality aversion, 1, and that gave him a very low discount rate, 1.4%. Okay, do the computation by yourself. You will find that this is what you get, 1.4%. Nordhaus is advocating higher discount rates, and what he does is to take myopia into account. So he takes a higher value for the pure time preference, and he takes about the same assumptions for the growth rate. This is just forecasting growth. And he takes higher values for the coefficient of inequality aversion. On considerations we can talk about if you're interested, but this is not so important here. And he ends up with values which are closer to 4%. So his favorite value is something like 4.5%, which is why I took 4.5% in my example in the beginning, right? So these values motivated my choices of the example in the beginning. So there is an important difference between these two guys that I want to insist on. Stern is saying the proper value of the discount rate should be an ethical choice. It comes from a social welfare function that we take, so that's the one we've been talking about here. And the parameters, especially the parameter for the coefficient of inequality aversion, that's an ethical parameter, and so on, and here as well. Whereas Nordhaus is essentially using the formula in the reverse way. He says, I want to end up with a discount rate that's not too different from the market interest rate, which he believes the relevant rate should be something around 4 or 5%. And then he reverse engineers the formula to find the parameters that gives what he wants. And in particular, this myopia parameter is deduced from the formula in order to get the rate that he wants, right? So you can use the formula in the opposite direction and deduce how much myopia you need to put in order to get what you want. That's called the descriptive approach in this field. And And so there is an interesting debate here that you may think about more. Should we rely on market rates or not for policies that have very, very long-term effects, right? So if we trust market rates, it means that you know what market rates depend on. They depend on decisions of people who invest for the near future, a few years, at most a few decades. Is that a relevant expression of population preferences when we look at very long-term impact over several generations? That's very contentious. So Stern says emphatically, no, we shouldn't rely on markets because over several generations, this is a totally different question, and there is no reason the market rates give us the right answer. Right? So this is the debate that prevails between these guys, and it's a big deal, of course, in terms of consequences for policies. So the carbon tax that they advocate, of course, are very different when depending on the values of the discount rate that you get. And the example I've given shows you how small or big the future looms in these things, depending on what you take as discount rate. Okay, so that's essentially the main thing I wanted to say. Now let's look back at what you have chosen. Remember, so if you look at your answers, you can compute the corresponding coefficient of inequality aversion that corresponds to that. And so we had a big success for the options C and D. So that corresponds to a coefficient of inequality aversion that is around the value that was chosen by Stern. And then when you get there, then you quickly get to very much higher values. So how is this done practically? So if you are math-oriented, I've done it using this function, which is the function that is standardly used. So it's a function that takes consumption and raises it to the power 1 minus the coefficient of inequality aversion. And you put a term in front of it because if this coefficient is greater than 1, you have a negative coefficient, and so the function becomes decreasing. To make it increasing again, you need to put a minus, a negative sign in front of it. Okay, now last slide, I want to emphasize that these are the main issues that we should think of when we enter this field. But there are other important issues. So one I have not talked about here is inequalities within generations. When you look at future dollars, it may depend a lot on who will get these future dollars. So for instance, climate impacts, are they harming the poor or are they harming the rich? This may make a big difference to how we want to discount the future. So we have somehow to put the two parts of this lecture together at some point, and I have not done it here fully. Another important consideration is risk, right? The future is full of unknowns, and so especially what happens is in this kind of computation, if there is a risk, even if it's a small risk, that the future will be poorer than us, then that risk looms large in the computation, right? Because why that? Well, because if the future is poor, then it has a high priority, right? So small probability of a high priority consequence, that looms large in the computation. So that's also something that justifies. So the more risk you put in the picture, essentially the lower your discount rate in your analysis, and that's something quite important. And finally, there is something I will essentially leave to the ethicist in our team, which is the question of the value of changes in population. There will be impact on the size of the population of long-term policies. We may have less people, more people as a consequence. How do we value the presence of population? So the criterion I've given here had this LT, so the size of the population. So it looked like the more people you have, the better it is. But essentially, this is a criterion that was designed for situations where the size of the population doesn't move. If it changes with the various policy options, then we have to have some opinion about that. And this is a whole field of ethical conundrums as well. Let me stop here. Thank you, and see you next time.